for this problem, we're given the region R is bound by the curve of the equation y equals sine 2x, the x-axis and the lines x equals 0 and x equals pi over 2. For part A, we want to find the area of the region R, and for part B, we want to find the volume of the solid formed when the region R is rotated through 2 pi radians about the x-axis. So we have an area problem and a volume of revolution problem. So let's tackle the area problem first. So we want to find the area. Now, it's an area bound by the curve and these lines and the axis. So to find the area underneath the curve, we're going to need to integrate. And our limits are given by these two lines. So our lower limit is 0, our upper limit is pi over 2. Now, because our limits are given in terms of x, it's a simple enough problem. So we're perfectly fine to leave our expression in terms of x. So we are integrating sine 2x, the curve, and we're integrating that with respect to x. So we need to remember, if we integrate sine, we're going to get minus cos of 2x in this case. And then you need to make sure that you divide by the differential of the 2x, so we're going to divide by 2. And we don't need a plus c because we have our limits of pi over 2 and 0. So then we need to substitute our limits in. So we've got minus cos of 2 times pi over 2, which is pi, over all over 2, minus in the middle, minus cos of 2 times 0 is 0, all over 2. Cos pi, you should remember, is minus 1. Minus minus 1 becomes a plus 1, so you've got a half. Cos of 0 is 1, so you've got minus a half, but it becomes a minus a half, which is plus a half. And a half plus a half, very nicely, is 1. So the answer for the area of that's bound by the curve y equals sine 2x, the x-axis, the lines x equals 0, the x equals pi over 2, it's just 1. So let's move to a slightly harder problem then, the volume of revolution. So we want to find our volume. Now you've got to remember with the volume, you've always got that coefficient at the start of your integral of pi. We have the integral between the limits of 0 and pi over 2 again. But this is where you need to remember that for the volume, not only do you have the coefficient in front of the integral of pi, but you also need to square your function. So in this case, we have a sine squared 2x. That's very important, which we're going to integrate with respect to x. Now, before we can integrate this, and we've looked at this earlier in the course, we need to remember, in order to integrate a sine squared function, we need to use some identities, specifically the double angle identities. So, if we remember from our double angle formula, we have that cos 2x is equal to 1 minus 2 sine squared x. So if we have sine squared 2x, we're doubling, so really it's cos 4x is equal to 1 minus 2 sine squared 2x. And we need to rearrange this to make sine squared 2x as the function. So you're going to have a half minus a half cos 4x, which is what we then need to substitute into our integral. So let's keep our coefficients, keep the limits. You got a half minus a half cos 4x, which we're integrating with respect to x. Again, keep the coefficients, and let's integrate our parts. Integral of a half becomes x over 2. The integral of cos is just sine, but we've got a minus there, so you've got minus sine of 4x over the differential, the 4x, which is 4 plus this factor of 2, so really we're dividing by 8. We don't need a plus c because we have our limits pi over 2 and 0. So we need to substitute in our limits. Let's keep pi on the outside. If we substitute pi over 2, we have pi over 4 minus sine of 4 times pi over 2, which is 2 pi over 8, minus in the middle, 0 over 2 is 0, minus sine of 0 all over 8. Sine 0, we should recognise is 0. Sine 2 pi is also 0, so 3 of our terms there have gone to 0. So all we have is pi times pi over 4, which is pi squared over 4. And that is our final answer for the volume of the solid form when the region R is rotated through 2 pi radians about the x-axis.